All right, here's our calculator homework video. We should have our calculators up. All these problems will involve calculator usage, but they also involve our calculus knowledge. So just because it's a calculator problem doesn't mean you don't need to remember everything we've learned in our calculus class, okay? So we'll start with a function with the value of f prime of 2. So there's two ways to do this, and I'm going to show you multiple ways to do every problem if it's possible. One way is to actually find the tangent slope generator here. E to the negative x has got an outside and an inside. The outside is the e to the power, the inside is the negative x, so the derivative is e to the power times negative 1. So that'd be negative e to the negative x. The derivative of cosine is negative sine. Remember, we're talking about the derivatives now. The derivative of 1 is 0, not x. Okay, so like we've been doing antiderivatives. Now that we're doing derivatives, you got to remember how to go back to the normal way of things. And then if we plug into, we get, negative 1 over e squared plus negative sine 2. And that's some value that we could plug in. Negative 1 over e squared plus negative sine 2. Make sure your calculator's in radian mode. This is very important. Always be in radians in this class. And we see negative 1.044, 5, or 1.044. We always leave our decimals rounded or truncated to 3 decimal places. I like truncating. You just write 3 decimals and leave the rest out. Okay? Or we can utilize n-derive, math 8. Our calculator will take 2 points, really, really close to 2. We go to math 8. There's n-derive. I'll go through the older formatting. We will plug in the function, not its derivative. It's like I'm taking the derivative of this. Comma, with respect to x, when x is 2. So a comma with an x and then a comma with the number that you're trying to find the derivative of. Your calculator will plug in 2 points very, very close to 2. Into this, it'll calculate the slope using the slope formula, and it gets that same value. But notice it's a little bit different than what we got. We got an exact answer. Your calculator gets an approximation because your calculator is approximating using a secant slope formula of 2 points pretty close together, but not infinitely close together. And we get our answer. All right. Now, this question is the first derivative function f. This is actually f prime. You can't really see it, but that's f prime. One is f increasing. Okay, this is very important. It's not when f prime is increasing. Something is increasing when its derivative is positive. So that's very important just to understand. Something is going up if its derivative is positive. Okay, increasing and being positive, not the same thing. Okay, a derivative being positive means the antiderivative is increasing. Okay, so f is going up if f prime is positive. Now we won't say positive, we'll just say greater than 0, that's positive. Okay, so f is going up if f prime is positive. I'm going to graph f prime. And I'm going to see when it's positive. Now, notice, if you graph it like this, it's going to be very tough to do. If you adjust your window so it's between 0 and 2, that might help. 0, x min, x max. We don't really care about the y's, mins, and maxes being from negative 10 to 10 because we just want to see when it's like above or below the x-axis. So why don't we go from like negative 1 to 1? We can see it looks like we have a 0, we are negative, a 0, we're positive, a 0, negative. Now we got to find these two locations to see when f prime is positive. Here's positive values. Positive values are above the x-axis. It's not I'm going up. It's that f prime is positive. I will also graph y equals 0. I will second calc find the intersections. I see there's one intersection at 1. Second calc intersect. I'll find my other intersection over here. All these values are positive. And I got 1.690. That's my answer. F is increasing if f prime is positive. Here, f prime is positive. Okay, it says the derivative of the function f is given by f. This should be f prime. So sorry. How many points of inflection does the graph of f have on the open interval from negative 2 to 2? Points of inflection occur when f double prime changes sign. Okay? If f double prime is positive, the original function f is concave up. If f double prime is negative, the original function is concave down. This is f prime. Now, we can look at two ways. We could graph f prime, and we can see when the slopes change. Because the slopes of f prime are sines of f double prime. The derivatives of f prime okay, so that's one way to do it. Another way to do it, and I'll show you both ways, is to find f double prime and see when the values change sign. Okay, let's do both. We're going from negative 2 to 2. I'm graphing f prime. I got x squared cos x squared. Adjust my window from negative 2 to 2. Okay. Now, f prime is this. F prime is increasing here. F prime slopes are positive here, and then f prime slopes are negative, and then they're positive, and then they're negative. There are 1, 2, 3 locations of points of inflection for f because there's 3 locations where f prime's slopes change. Now, you could find those locations by finding either the max or the min. So here's a max. We can say, you go second calc, max. You go to the left of the max. You go to the right of the max. You press enter one more time to guess. So here's one location, negative 0.927. Next location, second calc, min. Looks like it's going to be at 0. Let's just double check. Left bound, go to the left of it, go to the right of it. Yes, so this is essentially 0, 0. So I'm going to say 0. It's 2.512 times 10 to the negative 6th power. Move the decimal place over 6 times. 0.000002512. That's essentially 0. Remember, your calculator just guesses. Approximates, not guesses. Maximum, go to the left, go to the right. 0.927. So it looks like it's symmetrical. Okay, so there's one way to do it. The other way, we could find f double prime. Now you got to remember how to take the derivative of this. you have to use the product rule. Derivative of the first times the second plus the derivative of the second. This guy's got an outside and an inside. The outside is the cosine. The inside is x squared. So I'll have negative sine times 2x. So negative sine x squared times 2x times x squared. So there's f double prime. Watch out, if I graph f double prime, 2x cos x squared plus, this will be negative 2x cubed sine x squared. I'm going to see, we're going to change signs. I made a mistake. To the first and the second plus to the second. That was the first. 2x cos x squared plus negative 2x cubed sine x squared. That's right. But maybe like this is getting all messed up. You know what? If I go back to the other one, I wonder if there's more than negative 0.9270, 9.27. So here we're looking at these locations. You can see if I now find the zeros, second calc intersect. Find this zero, this is going to be at negative 0.927. Yep. This one's at 0, 0. I'm not going to check that. The other one, if you scroll up or down, you could switch between the functions. So you see I'm on the line now. This is positive 0.927, but look, it looks like we actually changed signs there too. So this is why this is a good question. We might not be able to see the signs changing. 1.850. Oh, this is interesting. 1.850, and I bet you the other one's at negative 1.850. And see, these are when f double prime is changing signs. It looks like it's at 4 locations. We were not able to see that. Yep. So let's go back. X squared cos x squared. Turns out there's going to be another minimum and maximum that we don't see. Ah, it's phenomenal. Watch if I adjust my window maybe to negative 10 and 10. Let's see. Yeah, right there and there. I adjust my window too much, and I didn't see that we have a min here, a max here, min, max, min. So second calc, min, go to the left. Go to the right. Right there. Okay, so which way would I do it in the future? I like to look at sign changes because obviously you can see, depending on how steep your graph goes and how quickly it increases or decreases, you might not be able to see on a regular window or adjusted window, which is what my problem was, where we have maxes or mins. But it's very easy to see when values change sign, when they cross the x-axis. So that's why I go with this. All right, negative 1.5 to 1.5. We got f prime. When is f concave down? F is concave down when f double prime is negative. F double prime is negative if you graph f double prime and see when it's negative, or see when the slopes of f prime are negative, or the values of f double prime are negative. Two ways to go about this. I'll do both ways again. We will have f prime. We're going to look at when its slopes are negative. We're going from negative 1.5 to 1.5. We may have to, okay, we see a lot of good stuff. We see that the slopes are negative here. The slopes are negative here. I can find the minimum here. I can find this value. It's probably 0 and the minimum there. So second calc min. Looks like it's negative 1. So from negative 1.5 to negative 1. And then it's going to be from 0 to what I assume is 1. Not the intersect, second calc, a min. I'm assuming this maxes at 0. And then this is a min at 1. Okay? So from negative 1.5 to negative 1, and from 0 to 1. Or we get a found f double prime. Now to find f double prime, we got an outside and an inside. The outside is e to the power. The inside is x to the fourth minus 2x squared plus 1. So this derivative is e to the power. This derivative is 4x cubed minus 4x. So f double prime equals e to the x to the fourth minus 2x squared plus 1 times 4x cubed minus 4x. Derivative of 2 is 0, so that's gone. We could graph e to the that times that. See when this is negative. We see it's negative until here. This is 0. Here are negative values of f double prime. So negative 1.5 to negative 1. And then we see it's negative from here to here. So double checking that this intersect is at 1. So here's negative values from 0, negative values to here. This is 1. Okay. Another f prime. When do we have a relative max? Okay, f, the original function f, has a max when f changes from going up to going down. F goes from up to down when f prime changes from positive values to negative values. Okay? We have f prime. All we need to do, and we can't take the antiderivative of this to be able to look at f, and that's very common for these problems. All we have to do is graph f prime and see when does it change sign from positive values to negative values, because that means f is going to be going up, then down. We're going from negative 2.5 to 2.5. I don't have to worry about the y min and y max. I really could just see from negative 1 to 1 to see when it changes sign. Okay, so let's think about this. F prime is negative. Yep. It's negative till it gets to a 0. Then it's positive till it gets to this 0. Then it's negative and that's positive. So right here would be the location. Because f prime's got positive values then negative values. That means f's going to be going up and down. And this is going to be at x equals 0.5423. If you recall, we used to do this by hand with our friend the number line. We'd say f prime starting at negative 2.5 and going to 2.5 was negative until, let's find this intersection. Negative 0.474. That it was positive until 0.542, just 3 decimal places. And then it was negative. Now notice, like, negative values, positive values, not going up, going down. Negative values, positive values, negative values until here. 1.395. Oops. Negative values, positive values. Signs of values of f prime tell us that f is going down, then up, then down, then up. This is the location of my max. I have 2 locations of mins. Next problem. F is defined. Here's f prime. Which of the following statements are true? All right, well, let's see. Sine x squared. That's f prime. We pretty much see everything here. We're talking about from 0.4 to 2.4. Okay. So, f prime is positive, then a 0, then negative. F prime is going up, its slopes are positive, and then its slopes are negative, and then its slopes are positive. I can answer all these questions. F has a relative max. That means f has to go up and down. For f to go up and down, f prime is going to change from positive to negative. Does f prime change from positive to negative? This is the graph of f prime. Here are positive values. Here are negative values, so yes. F has a relative min. That means f goes down to up. That means f prime changes from negative to positive. Does f prime change from negative to positive on this interval? No. F has 2 points of inflection. That's when f double prime changes sign from positive to negative. That's when the slopes of f prime change from positive to negative. Slopes are positive slopes, negative slopes, positive slopes. So positives to negatives to positives, 2 points of inflection, yes. So 1 and 3 are correct. Next. All right, some more, some different types of problems here. The line L is tangent to the graph of y equals cos x at the point k cos k, where k is between 0 and pi. For which value of k does the line pass through the origin? Great question. All right, so let's talk about tangent lines. L's got to be in this form. Y minus y1 equals some m times x minus x1. Okay, and we know that we have some point k cos k. So y minus cos k equals some slope x minus k. Well, what's going to be the slope at this point k cos k? And they really help you by giving you this. They really, really help you out. Well, we know that the tangent slope generator, which will be used in tangent slope equations, y prime is negative sine x. That's the derivative of cos x. So y prime at this k will be negative sine k. Okay, so I'll just put this here. So, for which value of x does the line pass through the origin? Okay, so passing through the origin means the y value is 0. So, I gotta think about this for a second. That's the point. That's the slope. I'm gonna draw a picture here. This will help me. I got cosine between 0 and pi. Cosine of pi is -1, so we're talking about here. I mean, oh, the origin. It's not an x-axis. It's the origin. The origin is the point 0, 0. I don't know if there's a point like that. If you're talking about from here to here, oh, there you go. Right there. Something like right there. Okay, origin, 0, 0. So I can plug in 0, 0 and solve this equation. Now, how do you solve this equation? How do you solve any equation using your calculator? You can graph y equals the left side, y equals the right side. And I bet you I'm somewhere between pi over 2 and pi because I can kind of see that's going to pass right there. So let's see. Y equals, I got negative cos k. You could use x's, okay? Don't worry about k's. And then y equals negative sine k times negative k. So that turns into like positive k sine k because the negative and the negative cancel. I'm going to adjust my window to be between 0 and pi. I'm assuming I'm going to see a solution somewhere between pi over 2 and pi because of my picture. There it is. Let's go back to like -2 to 2. That should cover it so we can see it better. Boom. That's going to be between pi over 2 and pi. .798. .798 is between pi over 2 and pi. Okay? Now, to confirm that this is true, if I looked at this equation with this value plugged in. As well as cos x, you should see a tangent line that passes through the point 0, 0. So I got negative sine 2.798. I should probably put in the entire decimal, but we'll be close enough. X minus 2.798 plus cos k. I'm also going to graph cos x. And we should see, there's the cosine graph right here. And here is my tangent line. Let's kind of zoom out. Zoom, trig. Yeah. So here's the cosine graph. Here's my tangent line. This tangent line is passing through the origin. What I was thinking at the first, which tripped me up, is that it was just like an x-intercept. So I was thinking just y equals 0, but origin is very important. Origin is the point 0, 0. So you plugged in 0, 0, you solved. This is a tricky problem. Took me some time to figure it out because of this little mistake. So hopefully you watch the video and you understand why. When do the graphs of f and g have parallel tangent lines? Parallel tangent lines mean f prime values will equal g prime values, right? That makes sense. So when was our tangent slope generators going to generate the same tangent slopes? Now we got to understand why the derivatives of e to the 2x times 3 ends up being 6e to the 2x rather than 3e to the 2x or 3 halves e to the 2x. With derivatives, it's the derivative of the outside times the derivative of the inside, the 2 times the 3, there's f prime. G prime, 18x squared. Excuse me. When will f prime equal g prime? Let's graph f prime and g prime. I have no idea like what are, I mean, there's probably going to be 1 or 2 locations, but I don't know what my boundaries are going to be, so I'm just going to kind of wing this. We have a parabola and a exponential function. There might be 2. Yeah, let's zoom standard. So you can see there's one here. There's going to be another one there. Let's adjust my x's so that we shrink this a little bit. But let's really explore the y's. Maybe up to 30, maybe some more. Oh, actually, no. There's only one location. It's not going to come up because we know e to the x grows faster than x squared. So these two are never going to intersect. I should have known that. My bad. It's just going to be at this one location. Negative 0.390. If you graph the original equations, 3e to the 2x and 6x cubed, you'd see at negative 0.390, this tangent slope, and right here, negative 3.90, 0.390, that tangent slope are going to be the exact same. And you can do second calc dy dx if you wanted to. Type in the value. You see it's like 1.617. Go to the other one. Second calc dy dx. Go to the other one. Negative 3.90. Negative 0.390. Oh, sorry. 2.737. That's the slope. Let's go to the other one. Second calc dy dx. Negative 0.390. 2.7. Yeah. 7 something. Right there. Okay. Next question. Fuel consumption is modeled by F of S, where F is the speed of the car. So depending on how fast you go, this is how much fuel you burn. If the car is traveling at 50 miles per hour and the speed is changing at a rate of 20 miles per hour squared, what is the rate at which fuel consumption is changing? Might seem like a tricky question, but if you ever see like what is the rate, you're thinking derivative, like the rate of change. So F prime of S would be rate at which fuel consumption is changing. The car is traveling at 50 miles per hour, so that's S, and its speed is changing at a rate of 20 miles per hour squared, so that's ds dt. Okay, very interesting. When I take the derivative of this, and it's not that hard to do normally, but I don't have to. I'll show you two different ways. We got an outside and an inside. The outside is e to the power, great. The inside, I'm going to write as 1 over 20s minus 1 over 2400 s squared. And I got a 6 here. The derivative of the outside is not that big of a deal. The derivative of the inside is actually not that big of a deal. We got 1 over 20, and then 2 over 2400, which is what, 1200? S, but each derivative of this should have a ds dt, which means you need a ds dt multiplied by the product of that. So like, let me show you. You can either have 6e to the, I'm just going to leave it as the power, times 120 ds dt minus 1 over 1200 ds dt, s ds dt. But you could factor out that ds dt, and it ends up on the outside. Okay? And then you could plug in the values. So f prime at 50 equals. So this is like, I think, the more complicated way. I'm going to show you a different way to get this answer. 6e, got to be very careful, to the 50 over 20 minus 50 squared over 2400 times 1 over 20 minus 1 over 1200 times, it's going to divide first, then multiply by the 50. I'm not worried about that. Times ds dt 20. Okay, I get 4.298. That ends up being miles per gallon. So it's like miles per gallon times ds dt. Oh, miles per gallon times gallons times s is miles per hour, and ds dt is miles per hour squared. No, I'm not going to worry about the units for the fuel consumption changing. I'm sure it's like miles per gallon per hour squared or something like that. Anyways, another way to get this answer is using and derive. If you take the derivative of 6 e to the s over 20 minus s squared over 2400 with respect to x, at x equals 50, we get this answer. I needed to close these parentheses. If you took this and multiplied it by ds dt, you get the same answer. Okay? So, or the derivative of f of x at x equals 50, f of s, when s is 50, times ds dt, you have gotten the same answer. Now, it's tricky to think about and do. That's a tricky problem overall, but especially the units. I don't even know the units. Somebody can tell me what the units are. All right, next problem. Intermediate value theorem. It's good. Intermediate value theorem talks about if we know 2 points and a function's continuous, you're going to have to cross through all. It's how we can guarantee that like zeros exist on functions. You might not be able to find a zero, but if you know you have a negative point and a positive point and your function's continuous, it might have sharp points, but as long as it's continuous, you know you're going to have to cross through that value. That's the intermediate value theorem. So we're going to graph this. We're going to see like which one of these do we cross through? Which one of these numbers? So we got to be able to graph the function. We're not going to worry about the derivative of the function. Just x to the fourth plus x cubed plus x plus 1 divided by 380 minus natural log of x squared plus 1 divided by 2. We're looking from 10 to 12. I'm going to look literally from 0, probably negative 1, all the way up to 68. I messed up with the window range. 10 to 12. Okay, so look at all the function values. The function values start at 29. They go all the way up to about 60. We are guaranteed to cross, and we do, 42.421 somewhere. It's going to be somewhere between 10 and 11, 10.98 and 11. So that's the intermediate value theorem. That's a good review. What is the instantaneous rate of change? The same as the average rate of change. Recall, rates of change. Average rate of change is the slope of a secant. Use the slope formula. Instantaneous rate of change is the slope of a tangent. That's not a good tangent slope. Average rate of change equaling instantaneous rate of change is guaranteed by the mean value theorem if the function is differentiable. This is the mean value theorem. Average rate of change and instantaneous rate of change will equal the average rate of change somewhere between. Okay, so between these 2 points, when will we see a slope like that? Somewhere down here. It's not a great example, but there you go. Okay, let's find the average rate of change. Between 1 and 4, this is the key point. You're talking about 1 and 4. I need 2 points, f of 1 and f of 4. F of 1 is 1 plus log 1, that's 1. F of 4, 4 plus log 4. Let's find the slope. Let's find the average rate of change between 1 and 4. We got, I'll write it down. 4 plus log 4. Minus 1 minus 1? Okay, let's just calculate that value. 4 plus log 4 minus 1 divided by 3. 1.462. I'm going to write out all the decimals. That way I find the exact location. You don't round until you get a final answer in this class, okay? Instantaneous rate of change, IROC, will come from a tangent slope generator. 1 plus 1 over x. We will find out when does 1 plus 1 over x generate a slope of 1.46209.812. To solve that equation, graph the y equals the left side, y equals the right side. 1 plus 1 over x. 1.46209.812 graph, window, zoom, standard. Right there. Second, calc, intersect. We are guaranteed to have this location by the mean value theorem. This function is differentiable between 1 and 4. We got 2.164. All right, that is it. Thank you.